Greetings everyone. Welcome back to Multivariable Calculus. Professor Simon here, ready to talk about multivariable functions. You already have an idea of what a function is. I'm sure you've been doing them for several years with several other math courses ever since high school. Or maybe you're in high school and you've been doing them for a couple of years. Either way, if you're at this level watching this course, you've done a lot of functions. Okay? So now we're just going to take that same idea and tweak it just a little bitty bit, right? So a function, as always, is an input-output machine, right? It's a mathematical construct that takes in some input and gives back some other output, typically with numerical values on both ends, right? Doesn't necessarily have to be, depending on what logical structures you want to set up, but here it's going to be, numerical values. Okay? So typically you've been dealing with functions like y equals some conglomeration monster mess of x's, which means that your domain is some subset of the real numbers, right? Now I put maximum possible here is the whole set. This double line R is the real number system. In other words, the number line, right? And that function does some process and outputs a real number also, right? Okay, so then it goes from R to R, basically, is what we say. A multivariable function is still the same idea. I'm still giving in some input values, plural, hence multivariable, okay? But I'm still only expecting one output, and this is key, okay? So you'll notice on all of the ranges here, they're all still just R, right? One single number output for each one is what we're still expecting. But what changes is the domain on each of these functions, okay? They're called multivariable because we're accustomed to having only one independent or input variable. Okay, I know before you had y's and x's, but that's not considered multivariable because you still have only one independent. Right here, z equals a function of both x and y is actually two independent variables. They can both vary. All right, that ups the scheme of things here. Okay. That's called a higher degree of freedom, if you will. They use that a lot in statistics and things like that. But in any case, I have more than one input variable, which changes the type of domain that I'm going to be using. The domain is R2, is what we say. What that is the XY plane of points. So an input here is not just a value, it's an ordered pair. I will be inputting an XY pair of values, and that's what my domain now consists of. Not a number, not just two numbers. My domain is a set of ordered pairs, but the output is still a single number, whatever z happens to be calculated to be. Okay? So the multivariable functions that we'll be dealing with, you'll have your domain is in the XY plane. It might be the whole plane, or it might be a subset of it, but it'll be in the XY plane. And then you pick points, and whatever those points calculate in the function will be the z value that will go above or below that piece of the domain. Okay? So that's where you get your surface from. My domain is two-dimensional, okay? And then as I get the z values off of that two-dimensional shape, I'll get a three-dimensional surface flowing through space, right? Next stage up. We, in this course, also talk about three-variable functions, okay? Which technically means that there are four variables. W would be your dependent, and X, Y, Z independent variables, right? So then my input would be a point from 3 space, R3, right? X, Y, Z ordered triple is an input, okay? And then, of course, the output is still one number, whatever the W happens to calculate from that equation. Let's look at some examples of each of these sizes of functions. Okay? Here's the functions that you're accustomed to, right? Some function of just x. And I'm defining it on just the 2D system of x and y. Okay? So y equals ln x plus 7, if you will. My domain is a subset of R1. R1 is just this x-axis number line. That's what R1 is. Just this number line here. And that's where my domain is. You'll notice from -7 on up, right? Those are all values that my x can be. So that's my domain here. Set of all x's such that x is greater than -7. Okay? Now, multivariable. F of xy is equal to square root of 4 minus x squared minus y squared. If you put z here instead of f of xy, that's just as fine. And you'll notice whenever I do these in GeoGebra, that's exactly what ends up happening. I end up putting z there so that GeoGebra will treat it properly. And then GeoGebra will also name it as a function once you do that. Okay? But if there was a z there, by the way, notice that I could square both sides and then add these over, and what I'd have is x squared plus y squared plus z squared equals 4. So this is just a sphere. However, it's the positive square root here only, not both, which means I'm only getting the top half, right? The top hemisphere of the sphere with radius 2 centered at the origin. Okay? My domain is the flat image, the shadow underneath that surface, right? This circle centered at the origin with a radius of 2. This is my domain. My domain is the set of points. Now you see, this is the way these sets work. This right here tells you the structure of what you expect a single domain value to be. Here, a single domain value is an x value. That's what this says. So right here, a single domain value is an ordered pair xy, a point somewhere on this shape. Once you pick a point on that shape, you plug in the x and y, and you'll get the z that comes off of that, and then put all those together, you get your surface, right? So here my domain is the set of points such that they obey this. Now, why would they have to obey this in this case? Well, it's the square root, right? I don't want to do the square root of a negative number. So when I set this equal to 0, you'll notice that's x squared plus y squared equals 4. And I can have anything less than that because I can do anything inside, and I'll do the square root of a positive number. But if I go greater than 4, right, if this were greater than 4, then these subtractions would end up being some sort of negative answer inside of my radical. Okay? And of course, it should make sense to you that it's a sphere. The square root would hinder you to only being inside of here. Okay? So, another comment. Notice it is the plus only of the square root, not the plus and the minus. The same idea as when you were looking at functions over here. Over here, functions had to pass that vertical line test. You can sort of start to peel away from that idea a little bit, because we do have other coordinate systems where the vertical line test is not a test for functionality anymore. Okay? For example, in 2 dimensions, polar, you can use vertical lines all you want, and it doesn't matter how many times it hits. That can still be a function in polar, or even parametric equations. Sometimes you can write things in other systems as functions. So be careful, but let me just break it down right here for just a second. You can, in this rectangular form, still use a form of the vertical line test. If you have your xy plane and you draw a vertical line, if your surface hits the line more than once, then that surface is not technically a f of xy rectangular function. Okay? However, even things like full spheres, which wouldn't pass the normal vertical line test, a whole sphere would not, we can actually write the equations for spheres as functions either using parametric or converting it to another system like spherical coordinates. In spherical coordinates, as you saw in the last video, I could just put rho equals a number, and that's a sphere, okay? In which case I could then try to say it's a function of spherical variables, okay? Multivariable functions don't have to be just x and y. They just have to be something in the plane, okay? So I could also have f of r and theta, and it would still be a multivariate function. It would still be using the xy plane or a subset of it as part of the domain, okay? In fact, you could write this one that way by just putting 4 minus r squared, right? And then the domain would be r has to be less than or equal to 2. So you can do these in other systems, and it all works the same way. But you have to be careful that when you convert to another system, whether something's going to be a quote-unquote function or not. The pure definition of function really has nothing to do with vertical lines. That's just the test that we use. The pure definition is, if I give it one input, will I always receive the same output? In other words, one input should be mapped to only one output. In this case, an input is an entire point. And all of these points, the way I have this written and this drawn, are all mapped to one z value, right? If I put in an x and a y, I can calculate a z value, and it would only do the top half, and that's a function in this case. Okay, so take that same idea and go one more variable higher, right? If I have g of x, y, and z such that x, y, and z follow some sort of calculation, right? This is a function of 3 variables, is what we would say. Yes, I know there's technically 4 because I would put a w over here like I did over there. W equals all of this. And think about that. If I have a 4th variable, it's a 4D shape. Notice I don't have a graph here because we don't have a efficient way of just graphing 4-dimensional objects. We live in a 3-dimensional space. Now, we exist in 4 or more, depending on which branch of science you want to talk about. We live in more dimensions, but we don't really perceive very many of them, and graphing things with a time dimension can be more difficult, okay? I will show you some graphs in this section of pertaining to some 4-dimensional objects, but you just can't look at it all at the same time as the problem, okay? We'll use some other level surfaces and things like that. But you can still treat this like a function. I can still treat this algebra-wise like something that takes in an input and gives back an output, and it can actually still have some meaning, okay? Notice the domain is an ordered triple because x, y, and z as a group is an input for this function. Okay? The domain just happens to be this because I don't want this to divide by 0, right? If this was just x squared plus y squared plus z squared, I would have said all triples in R3, okay? In this case, I say all ordered triples from R3 such that z squared plus y squared is not equal to 5, so that I don't divide by 0 here, just in this case, right? So there's an example of a domain, and remember, one element of the domain is this group of triple numbers, okay? So in other words, a single point from 3 space is a domain point, okay? So imagine x, y, z axes, the whole 3D space that we're just in, and every single point all over the place is an input, unless it's, on this surface here, okay? Everything but the ones on the surface there. So just imagine you pick a point from space and you plug it into this function, right? Here you go, plug it into the function. And then it gives you some number, it's one number output, right? Still R1 for the range, okay? Still a single number output. So then what kind of a meaning do we put with that if I can't graph that number? Well, think of it kind of like this. What if this were a temperature calculation for everywhere in the room? I could give it a location, x, y, and z, And then the calculation would spit back the temperature for that exact point at every single point, right? I could pick a point, give me a temperature. Pick another point, give me a temperature. That's one example of how I don't need to be able to graph something for it to necessarily have functional meaning, okay? So I can pick anything I want. Imagine electrostatic energy or something. Maybe this could be a calculation. You pick a point, and it would tell me how much energy is in that point. That's a very crude way of talking about that, but you get my meaning. I can assign a function value to each point in space, and that's not me graphing it, okay? That's me just being able to make something useful out of this function, okay? And later on, when we're doing some applications and integration, we do have some of these 3D functions that we need to use as we move through vector spaces, okay? Spaces that have vectors all over the place. So we will be using 2 variable functions and 3 variable functions in this course, okay? And you just need to keep in mind what the domain actually is and why that makes sense, okay? Some of the things that we'll be doing will actually depend on the domain that you're using, okay? So you need to know if your domain is a single value, a point in 2 space, or a point in 3 space. Just wanted to give you a quick view of that function that we were talking about there so that you could see what the shape was. Notice it is the top half of a sphere. And as we said before, if you look down at it, you can see the domain is this circle and everything inside of it with a radius of 2 and less. Next, we need to talk about another tool that we use to analyze the graphs of multivariable functions, okay? Whenever you're in your old school 1 variable functions, you would plug values into x and get out a y, and then every once in a while you'd also plug a y in by setting it equal to the function and compute out an x, that sort of thing. In multivariable functions, plugging in an input is giving it a point and then getting out a single number, which is what you'd expect from a function. Input, get a number, output. But in multivariable functions, doing the opposite, putting in an output, you don't necessarily get a input back. In multivariable, you might get a collection of points, which would be a curve. So that's what this is. We're going to talk about level curves. If we pick values of z, right, then basically what you're doing is you're picking a horizontal plane, and you may have some sort of graph where that plane intersects through the graph, would make an intersection curve. And that curve is called a level curve because you have different levels of z that you could pick the horizontal plane for, see? So for example, if I have something like f of xy equals 4 minus 4x squared minus y squared. It's an elliptic paraboloid, right? Facing downward like this. So let's say I pick the plane z equals 4 and say, hey, what's the level curve at z equals 4? Well, let's do it both ways. Let's look at the graph and let's look at the function, right? On the graph, if I draw a level curve, if I draw a plane at z equals 4, right, something like this, it would hit the top of that paraboloid, and it would just be a single point, right? So at z equals 4, if I put 4 in for z, right, I would get something like this. Like this. And the result of this, I subtract 4 from both sides and I'd get 0, and then I could multiply by the negative, and basically I'm getting 4x squared plus y squared equals 0, right? And since these are both squares, really the only thing that I can get from that is the point 0, 0. Okay? So in this case, the level quote-unquote curve is only the single point at the tip right there, where z equals 4 and x and y are both 0. Okay? Now what about z equals 2? Well, if I were to, at z equals 2 right here, make a slice with a plane, like so, right? It would hit the paraboloid straight through the meat of it, right? And then what I would get is an ellipse. I would get the ellipse that it sliced through the cup there, right? You got the, or the bowl, whatever you want to call it, right? You got the bowl, and it would slice right through the middle of it, but then that just means you'd get the cross section at that level, right? I'd get that ellipse. Well, watch. When z equals 2, I have 2 equals 4 minus 4x squared minus y squared, which if I subtract the 2 and then add my variables around, I'm just going to get 4x squared plus y squared equals 2. And of course, you know, you could go further if you wanted to graph it really accurately. You could divide by the 2 because you could see it's an ellipse and you'd want it equal to 1 and get your a and b and stuff like that. But just notice, it is an ellipse, right? Where the x is actually going to be smaller than the y, and that's exactly what's happening, right? I have the x going here and the y going here. And then what about z equals 0? Well, z equals 0 is the xy plane. That I already have drawn in there. The xy plane is slicing, and that's where I have this xy trace right here, right? The xy plane trace is that ellipse right there. And sure enough, if I put in z equals 0 into the function, I have 0 equals 4 minus 4x squared minus y squared, which is 4x squared plus y squared equals 4. Again, an ellipse. And then you could have the x being 1 and the y being 2 squared. And that's why you have the 1 and the 2 the way that's drawn. Okay? So at each slice, I had a different sized ellipse, basically. Right? And you can see that. The further I go down, the larger the ellipses get. Right? Another way that we inspect these is we would take several of these and draw them all together on a XY plane. In other words, imagine I could take this thing and rotate it so that Z comes out, and it's like I'm looking over it at the XY plane, right? See right here, Z would come out towards you. Okay? And if I graph all of these ellipses, I would start with the point 0, 0, that would be here, right? Next, 4x squared plus y squared equals 2. My x would be the square root of a half, which is like 0.7, which is here and here. And my y would be square root of 2, which is 1.5-ish here. So it would look like this. Like this. Okay? And then the one where z equals 0 would be where y is 2 right here and x is 1, like this. And we could keep going with this. Just imagine this thing gets larger. I can go lower. I could pick the z levels to be like -2, -10, and just use your imagination. This thing is an elliptical paraboloid, right? The ellipses are just going to get bigger as the parabolas spread out. So imagine the more slices I get, right? The more ellipses I get. Okay? Here's another thing I need you to notice. The jump from 4 to 2 is the same size jump from 2 to 0. But look at the size of the gap between these. Between the point and the first ellipse is way bigger than the distance from the first ellipse to the second ellipse there. And what that's indicating is that the slope, basically the incline of the sheet is getting steeper, right? The closer those things get together like that, even though it's the same gap in the levels, that means the thing is getting steeper, right? And you can tell that's exactly what's happening. This thing is kind of slow at first, and then it, the parabolas get steep like that. Okay? So this is one of the tools that we use to analyze multi-level graphs like that, so that we can look at it on a 2D plane. Okay, so the example I have over here is sort of a multi, right? These are all different things that would come at you when you have a function. So here's a function. These are different things that they would ask you, like what's the domain? Find the value at this, find the value at that, and so on, right? What are the level curves of this? And we can analyze this function, okay? So let's start with the domain. I don't see any square roots. I don't see any logarithms. I don't see any restrictive things with asymptotes like tangents or inverse secants or anything crazy like that. All I see is that division. It's definitely going to have a problem when I get a division by 0, right? So where is this thing going to be equal to 0? That's going to be the indicator for your domain. The domain is going to be the set of all. And remember, we're dealing with a 2-variable function here. So my domain is points, right? These are my objects. And such that they obey this next rule, x cannot be equal to negative y. Or you could put x plus y can't equal 0. Either way. And that's going to be my domain there, right? It'll be all of the entire xy plane. All of those points are domain points, except x can't equal negative y, right? So it'll be a line through the x-axis there. Not the x-axis, through the origin, right, with a negative slope of -1. Okay, function evaluation, right? Here, I'm just plugging in values into the function. I've got 2 times -2 times 2 over -2 plus 2. Uh-oh. I'm getting a division by 0. Undefined. Right? That must have been on that one line that's not in the domain, right? -2, 2. X is the opposite of y. Definitely. Okay, g of 5, 3. 2 times 5 times 3. 5 plus 3. So I've got 30 over 8. Or 15/4, right? Okay, so putting in an input, getting out an output, works just like any other function. What are the level curves? This is the opposite, right? I'm going to pick an output, and we're going to see what the level of that output would be. I don't have a 3D graph working for me this time, so let's actually go through and evaluate what this looks like. Notice, I start with a couple of examples, and then I go generic to see if I can maybe make a pattern out of this thing. And sometimes that's what you'll want to do. Okay, so let's start with z equals 0. 0 equals 2xy over x plus y. If I multiply both sides by x plus y and divide by 2, I'm getting 0 equals x times y. Right? Typical with fractions equal to 0, you end up with just where is the numerator equal to 0. And this gives me 2 separate answers, right? Where x equals 0 or where y equals 0, but not both at the same time, right? Because 0 plus 0 would give me a division by 0, right? So it's x equals 0 or y equals 0, and it's an exclusive or. If you're familiar with your operators there, you can say XOR, right? It's the exclusive or. Must be one or the other, but not both, right? Okay, so that's the level curve. If I were graphing this level curve right here, I would have the axes basically as my first two level curves there. Okay, z equals 1. 1 equals 2xy over x plus y. Multiply both sides by x plus y. So I have x plus y equals 2xy. And to make this something that we would recognize how to graph in 2D, let's go ahead and get y by itself, right? So I'm going to subtract the y. I'm going to factor out the y. And then I'm going to divide by the 2x minus 1. So that's definitely something that I could recognize and graph. That's a rational function, probably some sort of hyperbola, right? Because it's got a vertical asymptote, and I can see it has a horizontal asymptote as well. Okay. And then let's get the generic one here. Where z equals k, I'll have k is equal to 2xy over x plus y. I'll multiply the x plus y over just like I did here, but it's times k this time. So I'll have kx plus ky equals 2xy. And then I'll go through the same process as I did over here. I'll subtract, I'll factor out the y, and I'll divide. What I'm going to end up with is y equals kx over 2x minus k. Okay? And then you can just try to insinuate from there what your level curves would have to be, right? So let's just notch a few of these down and see if we can get an idea of what's going on here. Okay? So my first two, x equals 0 and y equals 0, but not the origin, right? So I'll leave the origin as an open circle, but definitely graphing the two axes here, right? That's my first level curves. X over 2x minus 1. Well, that's a rational function that has 0 as an intercept, because that's where x is 0. Has a vertical asymptote at 1/2, because that's what will cause division by 0. And it has a horizontal asymptote of 1/2 also, right? Because x to the 1 is the same. And if you do the limit as x goes to infinity, those are the survivors, you get 1 over 2. Okay, so we're looking at a function, and I'm just going to draw a couple of temporary asymptotes here for this guy. The temporary asymptotes would be 1/2 and 1/2, right? Like this. Okay. It goes through x equals 0 this time. So it would hug like this, hit the 0, and then hug like this. And then it would be up here also. Right? Like that. Now let me take away the asymptotes because those are going to get in the way of the other level curves that I'm about to do. Okay. So you can see what happened is from on this end, right? From here, from the axes, it expanded outwards, right? And on this side, it sort of moved this way. Well, let's look at it generically. If k was 2, right? I would have 2x and 2x minus 2. My asymptote would again be 1 for the vertical, and then 2 over 2 would also be 1 again for the horizontal. You should see a pattern going on here. Notice the horizontal asymptote for each of these is going to be k over 2, and the vertical asymptote, I should say y equals. The vertical asymptote is also x equals k over 2, the way those work out. Okay, and so what that means is every time k becomes a larger positive, the little center of those moves up another point, right? So it's like the asymptotes are going to keep moving this way like this, but they're going to stay the same proportion every time. They're going to be here, right? The two asymptotes are going to be right here like they were, and then they're going to move here, and then here, and then here, and then here. So what's going to happen? I'm going to get another piece of the hyperbola over here, and then to that piece I'm going to get another one over here, right? That works the same way. It's going to hit here, and it's going to hug out here. Because it has to still go through 0. Because look, 0 is the only thing that makes the top 0. I still have the intercept of 0, 0 every time. The only time that that's not true, right? Well, of course, I can't have it in the actual function, right? But these two have to skip over it as well. Okay? So that's part of the problem that we have here. This should be a whole no matter what. Okay? But all of these curves that I'm graphing don't have a problem with it. Right? The level curves don't. But the original function does have a problem with it. Okay? So again, as the asymptote moves that way, you know I'm going to get another curve. And then another one. Right? What about when k is negative? Right? We didn't even think about that. When k is negative, I'm still going to have this same relationship, but my asymptotes are going to become negative, right? So what's going to happen? They start here, and then they'll get more and more negative. They'll just start gravitating the other direction. So what do we get? We end up with the hyperbola is doing this instead. Here and here. And then if it moves further out, I'll get another one over here and another one right here. Right? Like that. Okay? So your hyperbolas are shifting back and forth basically, right? But some of them will go out this way and then other ones will go out this way. And it has to do with whether k, which really k is the z value, right? Being negative or positive. Okay? So keeping track of that, I'm thinking to myself, okay, if z is coming out of the board here, then those level curves that I drew in blue when k were negative, right? Those are underneath the plane. And then the ones I drew in red here, those are above the plane. Okay? So I've got a sheet of this thing coming out of the plane in this region just right here and in this region, right? They're coming out right here. And then just the opposite, I have this piece going in and this piece coming out, right? Do you notice how these are sort of sticking together here, right? Remember what happens when the pieces get closer together, right? It gets steeper, right? So the piece that's going in right there, right? It's shooting down. And this piece right here that's coming out of the board is shooting up because these are getting closer together. Whereas these are kind of spaced out sort of evenly. It's gradually coming up on this piece. It's gradually going inward on this piece here. Okay? So no, I don't have the 3D graph working for me here, but you can tell a lot of information just by graphing a few level curves and maybe even finding a pattern for them. All right? So I want to show you what this looks like for real. Go take a look at GeoGebra. Let's get a close-up look at these two shapes that we were just doing the level curves of. Here, I've got the function f is 4 minus 4x squared minus y squared. As we saw from my semi-decent graph, it is a elliptic paraboloid. And if I start doing level curves, it's like I'm going to start slicing it with planes. So like z equals 4 right here, you can see is a horizontal plane to, or it's parallel to the xy plane really, is what makes it horizontal there. But as you can see, it just barely nags the tip of the paraboloid there. And you can see the intersection is this point, right? Okay, if I move down to z equals 2, you can see the plane slicing through the meat, as we said earlier right there. And his intersection is an ellipse, just as we saw. And then at z equals 0, that's basically the xy plane, right? You can already see it. It's got the shadow in there. It hits at this ellipse here, right? And you can tell that the ellipses keep getting larger as they go, and they should, right? The lower down if I keep slicing this thing lower and lower. For example, if I were to slice it at z equals -2, right? And then I were to intersect that, right? Then you could also get something like that. There we go. See it a little bit better now. Right? So as I slice further and further down, I'll get larger and larger ellipses. Also, the contour map that we did, if you have the Z coming out at you, there they are. There's the level curve graph, right? The point in the middle, and then the ellipses as they go. And as we were saying before, notice that even though these are the same amount of Z distance apart from each other, as you go further and further out, these do tend to get closer and closer together. And that's because of the steepness, right? Look at, as the ellipsoid goes further down, you can see it does actually get steeper as it goes there. Okay. Also, I wanted to talk about the other curve that we did, which was 2xy over x plus y. Here's what that graph looks like. Well, mostly. Even GeoGebra is having a little bit of trouble with this one. You can see this little strip in the middle. We could probably erase that if we did more of a parametric approach, but I wanted you to see the equation here. It's not that big of a problem. You can't really tell from this angle anyway. But it is having a little bit of a problem, and that's mostly because of the way it approaches the origin there. See, it's really as it gets close to the origin here, which is not a valid point, right? It's starting to become sort of a vertical asymptote type of situation there. Okay. Anyway, so you can even see it in the graph. Look, so you can even see like some of the curves that it's even using to graph these are somewhat hyperbolic there, right? You can see the different pieces that it's using to try and do that. Its grid lines are being stretched in an asymptotic nature. But let's look at the level curves. Check this out. I have a sequencer that shows us several of the level curves at different levels of z, right? So right now this is every other value of z. So I have one here at 6, at 4, at 2, at 0, -2, and -4. So as you can see, right, those are the different levels of z, right, as it's slicing through here and on down and on down. Okay? But each curve is two pieces. This level curve that I'm pointing at right here is the z equals 2 curve. It's actually two pieces. You see, here's a piece of it over here, and here's a piece of it over here. Just like we were talking before, each level curve is a hyperbola. And if you look from the top view, like so, and let me turn off the function, you can see that those are exactly the curves that we were talking about before. The ones that are dotted means that they're below the XY plane. That's the way this thing graphs things of that nature. You'll notice if it's on the other side of something, it tends to dash it. Yeah, right? Because see, if I look beneath, they're not dashed. But if I look through the plane here, you can see they're dashed. So when you look at it like this, you can see our shapes were dead on. We were graphing these hyperbolas, right? And then we were graphing the ones where k is negative over here. Okay? I've even got this thing set up where I can do different densities. So for example, if I shrink this down to 1, that means it's only going to skip 1 in between each level curve. So as you can see, the slices are on every value of z, every whole number, 1, 2, 3, 4, like that. So I'm getting more level curves there, and from the top you can see how they're getting the same pattern shape that we were talking about before there.
And I can even cut it even closer here, look. Right? What's happening is I'm cutting it closer and closer together. I'm not going further and further apart with the z values. What's actually happening is I'm keeping the same z values and I'm just slicing a bunch in between. That's kind of too far. You can't see them separate anymore. Maybe right there at 0.2. Here's the original curve, right? And then look, those are the level curves, and it's only going every 0.2 level of z. See, it's slicing at every 0.2 increment, starting at 6, going all the way down to -6. Right? If you get enough of these, as you just saw a moment ago, you really just start to mimic the surface itself, right? But typically with these level curves, what we end up doing is graphing them something like this, right? And we probably wouldn't do this many, especially not by hand. Let's go ahead and back it off a little bit here so you can get the right idea. Probably would do every one like that. But that does give a really good representation of the surface itself.
To finish up this lecture, let's do the same thing, but with a 3-variable function. In the case of a 3-variable function, we don't get curves, right? Because we're doing collections of triples of coordinates, right? So if I plug in a value for the output of a 3-variable function, then I'll get some sort of equation in x, y, and z, which potentially could be an entire surface. All right? Think about how that makes sense. I have a 4-dimensional function, right? Picking a particular level, right, of the output is going to give me something in 3 space, right? Each one a different surface, okay? This is practically the only tool that we have at what the level that we're talking here for evaluating a function of this nature where it's 3 inputs and 1 output, okay? Now, there are other 4-variable functions that you study. In complex analysis, you do a lot of 2 and 2 type of stuff, and then that's completely different graphing and analysis that takes a completely different method. Here, though, we're talking about 3 inputs, 1 output. So the best way that we have to sort of investigate these is to pick level surfaces by plugging in values of W and then seeing the pattern that forms from the surfaces that evolve at each of those stages. Okay? So let's take a look at this one. Let's imagine that I have some sort of energy function here, right? So at any given point in space, x, y, and z, you plug in the coordinates of the point, and this thing will calculate the energy level of that particular point. Maybe it's some sort of field that's giving off some sort of energy, or, just whatever. Just use your imagination a little bit. Each point in space is assigned a level, a number, right? So each point in space has an output number assigned to it, and that's what this function gives, okay? So then these questions might be, hey, where are all the points that are energy level -1? Where are all the points that are energy level 0? Where are all the points that are energy level 1? So on and so on. Rather than trying to rack your brain with, okay, this is a 4-dimensional function, how does it intersect with my 3D space? And you could try to do it that way. I mean, that is sort of how we were doing the level curves, right? Where does the plane intersect the graph, and how does it affect the 2 space? Stuff like that. It's a lot more difficult to imagine these kind of graphs that way. We can't even hardly fathom 4-dimensional graphs, at least not straight up the way we do all of our other stuff. You have to have a pretty creative mind to imagine what a 4-dimensional shape would look like. Okay? So let's talk about it in the terms of energy levels, right? So every time I input a number for the output, I'm asking the question, what collection of points all have this same output, right? And I'll have an entire surface of points that will all share that same level of output. Okay? So W equals -1. I have -1 is equal to x squared plus 7y squared plus 3z squared. Since I'm adding and all of these are squares, they're never going to equal a negative number. X, Y, and Z would have to be imaginary, or at least one of them would have to be, at least, right? So this is a no-go, right? For us, it's undefined because it's not defined for our system. When W equals 0, 0 equals x squared plus 7y squared plus 3z squared. This is just the point at the origin, 0, 0, 0. Okay, so it's a single point that has that particular energy level, right? Or that particular output level, if you want to look at it that way. Then we go with W equals 1. So I have 1 equals x squared plus 7y squared plus 3z squared. And of course, if there were any manipulations necessary at this point, pun intended, then we would do that. But it's already in a pretty nice form. Remember, all the squares added up and it's equal to 1. It's an ellipsoid, right? I would have to make the 1 over 7 in the denominator and the 1 over 3 in the denominator here. But you could graph that ellipsoid, right? Through the 3 axes, finding the traces. It would just be 3 ellipses intersecting, basically, kind of looking like an M&M, if you will, right? But it's a really small one, right? At the 1 right here was already there. I didn't have to divide anything out. I didn't have to change any of the sizes. So we start with a point, right? That's the only point with this level. Next, it grows to an M&M, right? Some sort of ellipsoid that all share this level. And notice upgrading to 4 doesn't change it that much. As far as like the pattern goes, I mean, it will drastically increase the size, right? Because look, if I put this in the standard form, I have to divide by 4, which is going to be x squared over 4. 7 over 4, but if I'm going to write it in standard form, I'll put 4/7 all in the denominator, right? And then z squared right here will be 4/3 in the denominator there. Okay, so again, x is still the biggest distance, and it's actually going to be the same sort of proportion, right? I started with a point, it went up to a small ellipsoid, then it increased in the same size of an ellipsoid, and they all have the same center. They're all centered at 0, 0, 0. So you can just imagine, you have this point, and then these ellipsoids just grow around it. And those are going to be like your energy levels, right? Those are going to be the different collections of points that all share the same level of output, okay? And then just insinuate whatever dimensional analysis you want from that, right? If you're talking about something increasing in size like that, right? It's basically an ellipse that just keeps doing this, right? That's sort of like something that's a 4-dimensional ellipsoid-ish thing that's sort of like dipping into our surface. Well, not really an ellipsoid, if you will. It's more like a parabolic ellipsoid in 4 dimensions, right? Think about this with me for a second. In a normal parabolic ellipsoid, right? It's a bunch of ellipses, like the one we saw earlier, that start as a point and then get bigger ellipses, right? That's sort of like what's happening here. The W is to the 1 power, right? There's no square roots and no squares on the W part, right? So it's not actually a 4D ellipsoid. It's more like a parabola shaped, but a 4D one, right? Because I'm getting nothing but level surfaces that are ellipses as they get larger. It's growing like a parabola would. But if you can imagine sort of like a 4-dimensional paraboloid passing through our 3D system where we could only see part of it at a time, right? That's sort of like what's happening here if you want to go the dimensional analysis route on that one, right? Imagine some sort of 4D paraboloid that's just passing through, but we can only see 3 dimensions at a time, so we only see a small level curve of it at any given moment. And as the moments go by, right, the different pieces of it come by. Okay? So level surfaces. Every time you plug in an output, you're going to get some sort of surface, and all of the points in this surface have that same output, which is a connection for them to all be in a group together. And that'll become important even more later when we have some derivative and integral applications as well with three variable functions. Okay? So I hope this has helped you understand multivariable functions that we'll be using quite a lot throughout this whole course.
So just another quick look so I can give you a different aspect on this instead of just talking about it. We're going to look at that four-dimensional function by using the 3D level surfaces. Remember, I started with the equals -1, but that one doesn't exist. So at 0, right, you may have noticed, you may not have, there's that point right there where it started out. It's a single point. Then when it equals 1, you see it has this ellipsoid. And then at 2, it has this one. Notice it's pretty much the same proportion, and they're concentric. They have the same center. And then 3 and 4, you can see they're all just growing on top of each other, basically. 5, and then there's 6, right? They're just nested little eggs, if you will, right? And it's almost, you kind of look like they're getting a little closer together there, maybe. It's harder to tell, but you can definitely see a huge jump here, and then sort of a jump, but then this is smaller than that. They're sort of getting closer together there. But this is like an insight into that world of a four-dimensional shape. These are different level surfaces for different values of that fourth variable, the output variable. Okay, and another way of thinking of it is, instead of just doing each individual one here, is we could start with the smallest one, and then it should be more of a continuous thing like this, right? As the output value goes up, the object should just be continuously increasing. It should just be one surface connected to the next, one after the other after the other. And it should just keep going outward like that. So eventually the whole space would be part of some surface, because this thing will keep expanding forever. And the key is just which points are connected to which other points because they're on a same level surface. That's really where the relationship is here.